So let's go back to the workshop. So we have this second part now. So after this coffee break, so ROEE will be talking about the QA that is being done for the THEMO Observatory. So there will be another talk afterwards, and then we have another discussion, hopefully as good as the last one. So ROEE, the floor is yours.
All right. Thanks, Nuno. So we will now start the session about standardization of data, my talk now would focus on quality assurance of data. We saw that on the last in the last talk that this is indeed important, and people have to somehow rely on the data that they store. And this work is kind of a joint work that Nuno and I did together to offer a somehow novel quality assurance way that instead of looking at just the sensor itself, we look at cross sensors. But before going into that, I want to introduce the THEMO Observatory. That will give you also a perspective about the diversity of data that would lead to the quality, to the cross-sensor approach. So the THEMO Observatory is a collaboration between my university and Texas A&M. Texas A&M has been around in the observatory business for now, I think, 40 years. They have many moorings off the coast of essentially Texas in the Gulf of Mexico. And this is part of a project that is funded by the local Texas Ministry of Energy to monitor gas spills. And the idea is that when you have a gas spill, you know, like the Horizon incident, you need to know where the oil is going. So you need to know, you need to have a initial, in real-time assessment of where the current is going. And to do that, you can use models, but you need to have actual sensors in the water that are accessible now, not after collection. So you can have initial boundary conditions to solve the dynamic problem of the velocity field of the current, and that's where you can plan ahead how to contain the contamination. So that was the motivation of them to go into that field, and I think it's really nice that the way they are managing it, because the one who is delivering the funding is actually the Ministry of Energy, and it gets the funding from the oil and gas companies. So it's all kind of very transparent and very disconnected between the people who are actually doing the measurements and the people who are paying for it. And the idea of THEMO started up with kind of a similar motivation, because in Israel there was a discovery, and back then it was the biggest gas field in the world, and we started to actually extract it from the sea with lots of pipes and gas rigs that are being deployed, and some of them have been around for I think now more than 10 years. And the whole gas exploration was new, and it became clear that an observatory is needed to have, again, the same idea of real-time measurements on one hand, and on the other hand, to start to understand phenomena and how these kind of interventions are actually affecting the environment. So THEMO stands up for Texas A&M University of Haifa Eastern Mediterranean Observatory, and it contains 2 moorings that are always in water, and one that is in the lab as like a spare one. And the idea is to have a continuous time series. So they are exchangeable, and wherever we need to take one from the water to service it, we take the third one in at the same day. So there is a continuity of the data. There is a shallow mooring that is shown here. You see the mouse? Oh, no, I think I need to do that. Okay. All right. So there is a shallow mooring, which is roughly 11 kilometers off coast. It is right on the continental shelf at 125 meters. There's a deep canyon that goes down right here. So that brings in a lot of nutrients from the deep. The canyon goes directly to 500 meters, then kind of gradually to level of 1,500 meters. So it brings in a lot of nutrients. Very interesting soft corals are there. There is another observatory which we call the deep one, and that is some 30 miles off coast, and the depth there is 1,400 meters. And that observatory is actually in the economical water of Israel, so it's much harder for us to go there and visit it there. So we had to invest a lot in the maintenance of in the making of and the design of the mooring to make it really once a year. Go there, collect it, and that's it. Don't go there more than that. Okay, so the objective was to explore the deep sea, and we collect a lot of data. There is a scientific data, biology, sensors, oceanography, sediment traps, acoustics. I will go over some of them in a second. And then there is also marine technologies that are applied there. We visit the area with an AUV, we take images, we deploy acoustic devices that are there, like some sort of offshore lab. So this is in a way a platform that people can come and put their own sensor. So if one of you wants to put his own sensor on the mooring, it is possible. We are actually doing that. Okay, we have the sensors on the surface buoy, so that is about 4 meters from the sea surface, up on the sea surface, the height of the buoy. So there is a meteorological station there. There is several sensors that are on the frame of the buoy, so that's about 3 meters below the surface. And then there are sensors that are along the cable of the mooring. The shallow mooring is like that. It's basically a catenary mooring, so it goes all the way down to, as I mentioned, 125 meters. This is the location chosen for the shallow mooring. It's kind of upside down, so the more this area is kind of going up. So there's a canyon, and you need to kind of look at it the other way around that you're used to, maybe. And we are right here on a platform that is very interesting. There's a lot of current that goes down from the deep, and this is something that is called the biological pump that brings in nutrients, and there's a lot of life there. It's also very close to the border with Lebanon, so it's actually a marine protected area, and no shipping trawls are supposed to go there. So the lines that you see here are AIS measurements of ships that we looked around, and there's not too many that are going to this area. Right? And then the question was why would we want to put an observatory where we put it? So it's interesting in terms of the location. Bathymetry is interesting there. As I mentioned, there is a coral reef. The currents are not homogeneous. It's also have a line of sight to Haifa. So the university sits on a mountain, which is 500 meters above the sea level, and we have an antenna there, so we have a connection with the buoy, a real-time connection, so we can download data, fix problems. This is something that is happening all the time. And as I mentioned, it's away from the shipping routes, and it's a marine reserve. The deep mooring is more complex. It's what it's called an inverse catenary mooring. So it goes down deep to roughly 600 meters. Then there are buoys that brings it up to roughly 100 meters, and then it goes down again. And the idea is to give it flexibility in case of high waves. And we do get high waves. The highest wave that we recorded was 15-meter high. Next to that buoy, we have two other buoys that are actually submerged. One of them is a sediment trap that sits about 100 meters above the sea surface, sea floor. And that also has an ADCP on board. And we have a buoy that is only 40 meters below the surface with a profiler that profiles the water. It goes down every day twice from 40-meter depths to 1,400 meters depths. It goes down and up while collecting data with good resolution. Both buoys, we get access to that and we download the data periodically using acoustic modem. We have a Bentos modem there, and it downloads the data on a daily basis. On the profiler, whenever it goes up, it connects via inductive communication to the buoy at 40 meters, and then connects to the buoy, the surface buoy that has another modem on it, and that's about 500-meter distance. And then on the sediment trap, there is another Bentos modem that sits a bit closer, roughly 400 meters from the other direction of the profiler, and also send in some of the data, of the current data, but the processed one, not the real data, not the raw data, because it's too much. So the data on the buoys themselves includes salinity, and I mean on the surface, on the frame, it has salinity and it has ADCP that is looking down. So we cover the entire water profile using the profiler and the sediment trap and the buoy itself. On the cable, we have temperature measurements and the angle measurements that measure the temperature along the water column, and also the orientation of the sensor, so we can kind of understand also from that some of the force of the current. And the data is flowing up regularly using an inductive communication. So there's an inductive modem. Each sensor has an inductive modem, and there is an inductive receiver modem right on where the cable is attached to the buoy itself. And there was a big effort of trying to understand how to bypass the cable and get the data to a processor that is inside the buoy itself. We tried different ways how to bypass a swivel, and eventually we gave up after a lot of time that it got ripped, and we actually put it down the swivel, and still it works pretty nicely. This is the list of sensors that we have. So I mentioned ADCP. And there is a CDOM, there is turbidity sensors, there is conductivity and temperature, chlorophyll, humidity sensor, barometric pressure, waves. We have inertial measurements and gyro compass, and we solve essentially the orientation of the buoy in real time and assess the wave height, significant height, and we can also access the direction of the waves. So that's another thing we do. And in total, it's about 40 different sensors. The data from each sensors, we store the raw data and we average it every half an hour and send it to shore. And that data is being uploaded automatically on a server, and everyone can download from it. That's kind of the idea. So it's an offshore real-time, kind of real-time measurement. Okay, so we have an antenna that sits on the university. It provides us 30 megabytes for 30 kilometers. That's the shallow buoy. And about 25 megabytes for the deep buoy, which is roughly 60 kilometers offshore. It's a two-way communication, so we can also SSH the buoy. We can download raw data if sometimes we need. We can transfer files, scripts that we want to upload in two-way communication. And then the buoy actually also have an AIS system on it. It wasn't easy because the Ministry of Transport doesn't give AIS MMSI measurements to buoys. It gives it to ship. So I needed to convince them, and I went there and I told them I need an AIS. So they asked me, how big is your boat? So I told them, it's not a boat, it's a buoy, it's 2 meters. I said, okay, how fast does it go? It doesn't go, it's a buoy. But so eventually, with the help of some diplomatic help, we managed to get the MMSI, and we have an AIS point, which is also nice because we can get real-time information of where the buoy is, and we kind of tacked into the interface of marine traffic in order to evaluate, to give it like boundaries. So if it gets disconnected for some reason, we can have an alert, an immediate alert that something is wrong and we have to go there. And that actually happened twice. One time the buoy got swamped to Lebanon. Not a good friend now, at least. And we had to file a request to the UN to give it back. And there was a prisoner exchange at the border, and the buoy is back. So that actually worked. So the data is presented on screens in the university. That's actually a very good tool for education. Students are coming in, they see the data, they start asking questions, donors come in and we explain to them. So that's kind of an educational tool. And the university has a virtual server that keeps growing. As I mentioned, we already have about picobyte of data, and everything is being freely shared on a cloud service. Here is an example of stuff that we do with the buoy that we found. We found a tsunami that happened in Turkey by a change in the dominant period of waves. So that was really nice, and we actually found it on real time. The idea is that on the system itself, I will go into that, you can put in warnings. So you log into the system. It's a free login, and then you can choose sensor or several sensors and put a threshold. And the threshold can be upper or lower, or it can be a trend or a transient. Okay, and then if that data from that sensor that you picked, the threshold exceeds, it will send you an email. So that's kind of the way that the things goes, and that's how we detected the tsunami. We also use, as I mentioned, the THEMO as a platform. So that's a project that we did for the EU. This was called the Symbiosis, and we had several partners there. One of them was Vologics, who are here. And we developed a system that is some sort of cascade detection of pelagic fish using acoustic and optical sensors. And the idea was that the system is by itself, working by itself, so that's kind of a battery, the battery of the system, and that worked for a month before charges. And the charge can actually be from a buoy, or if you deploy it from a boat or something like that, you can also do that. Then there is an acoustic transmission, like a sonar. It finds if there is a moving target around. Then it classifies that movement, if that target is what we need, by understanding its trajectory, its motion, and its size. Classifying it by frequency diversity and comparing it to templates of different kind of fish. And then understanding if the fish is going to come close to the system. If it does, then cameras are being opened, and real-time autonomous detection is being made on the images themselves with tracking and classification of the fish. So here's an example of fish that we found. So that's a real-time system that tries to answer the basic question, how many fish are there in the water. So that's kind of the idea. So I want to show here, I think we have, no, I'm going to go over without showing the video, I think. We have 15 more minutes, right? And go into the quality assurance steps. So the motivation for quality assurance for developing that quality assurance was the understanding of the observation that data is indeed related. So we see here data from the THEMO Observatory that spans over a bit more than a month. And it shows you temperature readings from 86 meters, that's the blue one, 59 meters, that's the yellow one, and then the brown one will show you from 5 meters. And whenever there is a spike in the data, we want to see if that spike happened also in other sensors. If it does, then this is a real phenomenon, and we don't want to mark it as an outlier. If it doesn't, and the sensors are related, we may actually mark it as an outlier. So that's kind of the basic idea. And this is some sort of a diagram that shows you relations between data sets that are on THEMO. So for example, waves will be related to the barometric pressure. Because the barometric pressure is some sort of an indicator for the stability of the atmospheric environment. And then it's also related to the wind magnitude. So we have a wind measure. Of course, waves are related to wind. And it also may be related to the air temperature, okay, the waves themselves. So if we observe waves, instead of just saying, okay, I'm going to do the quality assurance based on the statistics of just the sensor of the waves, we will also look at these ensemble of sensors, which we can call them reference sensors. So the barometric pressure, the air temperature, and the wind magnitude. And if we know this relation between them, we can observe it and see if there is some sort of anomaly found in all of them or one of them. So that's the motivation for the work. And here is some more example for that. We show here chlorophyll measurements, and at the same time we see here conductivity measurements and temperature measurements, and they are all related. So that glitch over here, we may think, well, it's actually something is probably not right here. We may mark it down, but by doing that, we may actually miss on the important phenomena that we are looking for. These anomalies may be actually true, and they are very, very important. So, so it shows on the turbidity, it shows on the salinity, and it shows on the conductivity and chlorophyll. So it's probably right. There's something there. It's not just a glitch by itself. So this is kind of the idea. This is another example here. So the key idea for the quality assurance method has two steps, an offline step and an online step. In offline, we identify these reference sensors that we think are related. Okay, so temperature, conductivity, etc. And then how do we identify? Well, we can watch trends of the data, or we can do some sort of machine learning prediction to find relations between the sensors. That's kind of what we did. We basically first spoke to some experts and put on a list of sensors that may have some relation, have some understanding of relation, and then we checked them. We checked if they are indeed related. On the online step, we use some sort of an anomaly identification to find anomalies, and then we verify if it's indeed an anomaly by looking at the reference sensors. So also here, we did it using either a majority vote, like most of the reference sensors should agree it's an anomaly or not, or by doing prediction. The prediction was done using a support vector regression. So I'm actually going to skip that part, I think, and just show you the results. So this is reference results when you look at an assemble of temperature measurements, and you can see that the barometric, so the smaller it gets, the more related the sensors are, because that one shows you the error ratio in the prediction itself. So the barometric pressure was one of the sensors that the experts marked as maybe related to temperature. But actually, when we looked at the data over time, and we have lots of data, like 3 years of data collection for that sensor, we saw that there is actually not so much of a relation. But we did see that there is a very strong relation with the conductivity and with the salinity. So we use those, and maybe also the humidity. So we use those as the reference sensors. On the left side, we see the results for the raw data, and on the right side, we see the results for a wavelet transform of the data, and that is some sort of marking for transients that can happen. So also here, the salinity and the conductivity is shown to be very, very related to the data itself. That one is the anomaly detection. Anomaly detection is a lot of the time used by some sort of a CFAR system, right? Constant false alarm ratio system. But to do that, you need to know the statistics of the noise, right? It's a binary hypothesis detection problem. And finding the distribution of the data is a very hard assumption to make. So what I like to do is use distributions that have some extra parameters, but are shown to be general in a way. So they can actually somehow mark more or reflect more distributions than just a certain type. Sometimes these general distributions are also called heavy tail distributions. In this case, we chose the general Gaussian distribution. It has this parameter beta, which is some sort of a scaling parameter. When beta is 2, this becomes just the regular Gaussian. When beta is 1, it is the Laplace distribution. And anyone has an idea what kind of distribution we get when beta goes to infinity? Just to see if you guys are awake. So yeah, right, so uniform distribution. So a uniform distribution, that's what we will get. Actually, starting from beta equals 10, we already see that. So using that parameter itself, we can actually kind of reflect more distributions than needed. There are many other types that you can use. You can use alpha distribution, student distribution, Weibull distribution. All of them are complex. You have this nasty gamma function over here. When you integrate it, it becomes more nasty, especially when it's down. But essentially, it gives you this flexibility. So that's the methodology. We start with, as I mentioned, anomaly detection. So if there's an anomaly, we start looking at the data from reference sensor around the detected anomaly. And around can be an hour before and an hour after. Okay, it is a non-causal system because the data is being processed on the server itself, so we have this data. It's not exactly in real time. And we have, let's say we have n reference sensors. We have two options. One would be what I called majority vote. So we do anomaly detection, same anomaly detection to each one of the reference sensors. And then we put in a threshold, and if yes, then we validate that this is indeed, if this is indeed an anomaly or not, or if it's real data. If something is shown also on the reference sensor, we say, okay, this is real phenomenon. The other way is to use the reference sensors in order to predict what would be the data from the sensor that we are now testing, okay? So if there is a relation between barometric pressure and the conductivity pressure to temperature, we can use that data in order to predict what would be the data on the tested sensor. And then if we predict, we can compare this prediction between the actual measurement that we see. If it's far, then we say, okay, there is an anomaly here because we trust our prediction. That's kind of the idea. Okay, so this is called soft analysis. we can also combine the two in a way. And here are results that I show. So we look at two different ways to look at the detection. One would be looking at spikes of the data. So we have the measurement itself, Vn, and we look around it. So for Vn plus 1, Vn minus 1, so that would be some sort of a transient in a way. And the raw spike data is then being handled by the CFER detector. The other method is called the gradient, where we are actually looking at the gradient of the data itself. Both of these methods are basically part of a standard that is set by Ocean Network Canada in their system, in the Neptune system. So we basically adopted it. And here we show the ROC curve, so the receiving operator characteristic of the detector. On the horizontal axis, we have the false alarm rate, and on the vertical one, we have the detection rate. And we can actually mark the error because we had experts looking at the data, and that data is shown for an year and a half. So we did this tagging. And it shows us the different results if we're just using the change detector, or if we're using the majority vote, or if we're using the SVR prediction. And the results show that when we are looking at spikes, majority vote is probably the best thing that we want to do. And if we are looking at gradients, the SVR prediction was actually much better. And I think by the relation that we found is that if we go another step and do some deep convolutional network, we will get even better results. That result is actually nice because it shows you that the relation between the sensors to do this prediction, if it actually works, it means that we can identify relations between the sensors very nicely using this kind of simple mechanism. And that is important because as you heard on the last talk, there is a problem of disciplines, right? If I am a biology, I will look only on biology sensors. And if I'm an oceanographer, physical oceanographer, I will look only on those sensors. But a lot of the times, the things are related. And you need to learn from it in a way. So what I want to show now is a movie about THEMO. Let's see if I can share it. Sorry? What's that? To move it? Like to... Oh, okay, I see. Let's run it, and there's a...
2 years ago, the University of Haifa and Texas A&M University has signed a mutual agreement to construct and deploy a deep water mooring that will serve as the first Mediterranean marine observatory.
So ocean observing is an incredibly important aspect of science. The ocean controls the heat balance of the ocean and of the planet, really. The movable heat of the planet is in the ocean. So understanding how the ocean responds to various things, whether it's oil contamination, whether it's toxic algal blooms, whatever, the baseline of information needs to be developed. And that's really quite unique. There are only a few programs around the world that are doing that. And so this new technology that we have at our disposal should build a really important program for everybody.
Today, we are going for the first deployment of this mooring. We're going to deploy the mooring in northern Israel at depth of 125 meters. The deployment of the mooring is a new era in the exploration of the deep sea in the Mediterranean. The mooring is the state-of-the-art in offshore marine observatories. The data will allow researchers to conclude or to explore long-range observation from the sea, to update models about ocean currents, about temperature in the sea. It will allow the monitoring of the pollution of the sea and will serve as a warning system for possible earthquake and tsunami hazards.
The success of the joint development of the most advanced deep sea monitoring system in the Mediterranean basin, as well as the joint doctoral program to be signed with the University of Texas A&M, positions the University of Haifa at the global forefront of maritime research institutions in the entire world.
Okay, so it's like an echo. All right. So thanks a lot. That kind of concludes my talk. So if there's any questions, I'd love to answer.
So any question?
Thanks. Excellent talk. So I thought your equations there and models were quite empirical. You use the data, but there's also a lot of physics here and sort of oceanography, and I guess your results should feed back to that so that you can try to see where those models are off or what's wrong there. So, but you mentioned it a bit, but I guess you're trying to use the best out of all parts.
Right. So I think so first the whole idea of the cross sensor came up from a kind of a physics understanding of the relation between those sensors, that everything is kind of it's different sensors, but they will all show similar phenomenon. And I'm not a physics guy myself. I'm signal processing. But we had a large group of like 10 different experts from different fields that basically allowed us to form these reference sensors. That's for the quality assurance way. For what we are using the data of THEMO, that is mainly being used now for data assimilation. So people are using that data to kind of calibrate their models. I think this is kind of the, let's say, the common way of using this. What I wanted to argue here is that using the statistics of the data and this kind of prediction of relation between the data may actually reveal even more to it. Maybe from a statistical point of view, but it will serve as a motivation to start exploring that. Because in some of the reference sensors, we actually saw relations that were not indicated by the experts. So there is relation there, but it was unknown. So if we look at, and here in THEMO, it is just the number of relations is enormous. We have 50 different sensors, all looking at the same water body. And if you start exploring the relations between the data, not just the time series of one sensor, but trying to understand how things are related to one another, it doesn't have to be related linearly, mostly it doesn't. And it doesn't have to be also related causally. Sometimes it's before, sometimes it's after, sometimes you see the difference only a day after. But it will give some sort of an indication of how things are even more related than we thought.
Right. Other questions? Actually, we'll have some period of time after the next talk to discuss, so maybe we have some opportunity for a few minutes. But anyway, any question about the presentation?
All right. Thanks.